Welcome to The Explainer. Today we're going to do something a bit different. We're actually peeking inside a college engineering course to get our heads around the fundamental rules of energy. Yep, we're talking about thermodynamics.
And look, thermodynamics, it's not just some super complex subject for engineers. Think of it more like the invisible operating system for our entire universe. Seriously, you see its effects literally everywhere, from the fridge in your kitchen to the car you drive, all the way to the massive power plants that light up our cities.
So what is it really? Well, when you boil it all down, thermodynamics is just the science of how energy moves and changes form. It's all about this dance between heat and work that powers, well, absolutely everything.
Okay, so let's dive in. First things first, we gotta get the lingo down that engineers use. And it all starts with figuring out what exactly we're even looking at.
So first up, you've got to draw a line in the sand, so to speak. Inside that line, you have what's called the system. That's the specific thing we're studying, right? Like an engine. And everything else? Everything outside that little box? That's the surroundings. You know, this simple little separation is actually the very first step to solving any problem in thermodynamics.
All right, next up, we've got to classify the properties of that system, and they basically fall into two camps. You've got intensive properties like temperature or pressure. These don't care how big or small the system is. But then you have extensive properties, like volume or total energy. These totally depend on the size or mass of what you're looking at.
And this brings us to our first rule, which has a kind of funny name actually, the zeroth law. Yeah, zeroth. And when you hear it, it sounds almost ridiculously obvious, right? If object A is the same temperature as C, and object B is also the same temperature as C, then A and B have to be the same temperature. Simple. But believe it or not, this super simple foundational rule is the entire reason we can even have thermometers.
It's just a brilliant example of how a really fundamental rule leads to a tool we use every single day without a second thought. That thermometer? It's just acting as that third body, that C from before. It lets us compare the temperature of anything, say your forehead to a pot of boiling water, and know for sure that we're using a consistent, reliable scale. It's pretty cool when you think about it.
Okay, so with that foundation laid, let's move on to the first law. This is where we go from just measuring temperature to really understanding the flow of energy itself.
And here it is, the big one. I bet you've heard this before. Energy can neither be created nor destroyed, only altered in form. That's the first law. You can think of it as the ultimate unbreakable accounting principle for all the energy in the universe. No exceptions. You just can't create energy out of thin air.
Really, the best way to think about it is like a bank account for the universe. You can move energy around all you want, transfer it from one form to another. You know, like how a light bulb turns electrical energy into heat and light. But the total balance, the total amount of energy in the universe, it never, ever changes. It's a perfectly balanced budget, always.
So here's the takeaway for engineers. For any process, like say the complex cycle of an engine you might see mapped out in course notes, the energy books have to balance. Period. The energy you put in has to equal the energy that comes out. It's this perfect, clean calculation where everything just has to add up.
Okay, wait a second. If energy is always conserved, if it's never really lost, does that mean we can just keep reusing it forever with like perfect efficiency? Could we build a machine that just runs forever on its own?
I mean, that's the million-dollar question, isn't it? If no energy is ever actually destroyed, why can't we build a perfect, 100% efficient engine? One that takes every last drop of fuel and turns it into pure, useful work. Well, this very question leads us to the next law, and this one is profound and honestly, kind of humbling. It's the second law of thermodynamics. And the answer to that question? It's a hard no. A definite, absolute no. And the reason why? Well, it's one of the most fundamental concepts in all of physics. It literally governs the fate of the entire universe. And that concept has a name, entropy. The easiest way to think of entropy is just a measure of disorder, or randomness. And what the second law tells us is that the total entropy, the total disorder, of an isolated system, like our universe, can never ever decrease. It's always going up. It's this unstoppable march from order to chaos. This is what I like to call the cosmic tax. See, with every single energy transfer, every single time energy changes form, a little bit of it gets lost as low-quality, unusable heat. Now, it's not destroyed, the first law still holds, but it's scattered. It spreads out into the environment, and that increases the overall disorder. And that, right there, is why a perpetual motion machine is impossible. You always have to pay the tax. So, now that we've got the rules of the game down, let's see how engineers actually use them to build the world around us.
Okay, take water, for instance. These laws let us predict perfectly how it changes from a liquid to a gas. By controlling pressure and temperature, engineers know the exact moment water will be a subcooled liquid, when it'll be that boiling mix of liquid and vapor, and when it becomes superheated steam. And that superheated steam, that's the magic ingredient for generating most of the world's power.
And this is why it matters so much. These aren't just theories in a book. They're tested, they're proven, and they're applied in labs every single day to design, well, pretty much everything. We're talking about the engine in your car, the refrigerator in your kitchen, hydraulic turbines, pumps, heat exchangers, the nozzle on a jet engine, you name it. They all run on these fundamental laws.
And you know, when you see those handwritten notes from an actual engineering course, it all kind of clicks. You can just see how the abstract theory, all those squiggles and equations on a page, transforms into a real, practical, powerful toolkit for building and improving the world we live in. It's where the rubber meets the road.
So let's end on this one big thought. The laws of thermodynamics? They've governed our past, and they for sure govern our present. But that second law, that relentless, inevitable increase of entropy, it poses the single biggest question for our entire future. As all the useful energy in the universe slowly but surely winds down, how are we going to power whatever comes next?